Okay. Good morning, everybody. I'm Bob DeVance, K5CRX. We're doing a presentation in digital electronics for the McKinney Amateur Radio Club. We'll get this on recording, and you can review it at your leisure as we go along. So looking forward to working with you this morning. You'll see the slide presentation. We'll go through the slides, talk about what we're doing and what we're going to do. We have several projects that we will construct on screen as we go along, and you'll be able to see us build those as we go, and maybe do some troubleshooting and other things that just happens to come along when we do that sort of thing in live, as it were. So with that, let's go to the slides. Things that we're going to try to do today. We'll talk about some of the tools of the trade. One of the most important things will be our little breadboards. Let's see, do we want this over here? Okay, the little breadboard looks like that. One quick note on the breadboards, they're not all the same. This particular one has the power rails or the power connections down either side. And some of the boards have that actually split in the middle. It doesn't go all the way down. So you have to jumper the top half with the bottom half to get the power to go all the way down those rails. So that's just something to watch out for. That just depends on the board that you have. So that's not a big deal, of course. We have a little tool here for removing an integrated circuit. It just clamps over the circuit, lifts it out, makes it a little bit easier and saves your fingernails as you go along. Have a logic probe, which is a nice little tool, hooks onto the power, and it will tell us if we have a high or a low or pulse at a particular point on our circuit. The reason we don't use an oscope for this is that the oscope would work great if we were working with some higher frequencies, but we're running an on-off at about 1 second or thereabout rate, and so we don't really need an oscope for that. The logic probe works really well, however, for that. And of course, we always use our friendly little multimeter. Have to have a multimeter to know if we have voltage on our power supply. We will construct a power supply, for example, and we'll test that. Do have some handouts that go with all of this. We'll make those handouts available where you can download them if you'd like to do that. Of course, you can download the presentation even if you want, if you'd like to have that. Some of the things we'll talk about, digital thinking, which is a little bit different from analog thinking. How do we count just using ones and zeros in the digital world? Look at some digital circuits, and then, of course, we do the hands-on, which is why we call these classes hands-on. With that, let's go to the next slide. Okay, this is just a picture of a board that I set up initially. It's showing the little power supply circuit there on the top end of the board. Some little things to watch out for. We'll be working with I'm going to dump my components out here just a second here. Let me get those where I can get to them easily. The little bridge rectifier, as you can see in that picture, the very top side of that picture has two little squigglies there. That's the AC input lines. What we generally would like to, or what I like to do with those anyway, is put those two input lines on the top two rows of the little breadboard. That way it's easy to plug the AC transformer into there so we have AC coming in. You'll see that happen when we get ready to do that. And then we go down the rows on the left and the right. Traditionally, I will use red for the positive voltage and blue for the negative voltage. You can put both of those on the same side. I like to put them on opposite sides so I'm a little bit less likely to confuse which is which. It just keeps it a little bit easier it makes it a little bit easier for me. Also, you'll note those two ICs that you see there in the picture. The little one is a 555 timer IC. You notice it has a little dot in the upper left corner. That denotes pin 1. So counting back down from that pin 1, we'd go 1, 2, 3, 4, jump across to the other side and go 5, 6, 7, 8, and go back up, meaning that pin 1 and pin 8 are opposite each other. And that's traditionally going to be the case with these types of ICs. By the way, these are called DIP, dual inline packages. And you'll see these in a lot of the integrated circuits that we play with along the way. The other IC is a logic IC. You'll notice it does not have a dot, but it has a little notch in the top end of it. So if you look at the notch, you always know that go to the left, that'll be the pin 1 position. And on this one, it's a 14-pin dip. Pin 14 will be right across from it on the other side of the notch. Just some little things to look out for. Okay, that's an actual picture of what we're going to construct along the way. It won't look exactly like that, but it'll be fairly close as we go through. Looking at the top picture from left to right, on the very left, you'll see the bridge rectifier. That's that small, round, black device. Then the big round thing with the shiny center there is an electrolytic capacitor that helps to filter the pulsating DC that we create from the bridge rectifier. Then a little red LED there to let us know that we have power there. And then the little device just to the right of that, you just kind of see a little flat thing there, is the voltage regulator chip. And I put a second LED on it to let us know we have plus 5 volts regulated, because the logic and the chips that we're using do need 5 volts, and it needs to be fairly stable. And then you see the 2 chips and the number of resistors and LEDs and various things to make those things work. And we'll talk about each one of those as we go through and make that happen. Okay, this is a case of a breadboard that is not joined all the way down.
Getting your chips into the breadboard for the first time can be a little bit tricky. So placed right, they should straddle this middle divider on the breadboard, and they should be in the first row adjacent to that middle divider. And naturally the pins are a little bit splayed out and not vertical, and so if you just try to jam it in, it will tend to bend the pins and not fit in very well. So the first thing you want to do when you just pull your chips out of their package is to squeeze the leads together just a little bit. So you can just do this with your fingers, or sometimes it's easier to put the whole thing down on a flat surface and gently bend it in until the pins are vertical. Okay, once that's done, then you should be able to pop it right into place on the breadboard and push it all the way down. Getting the chip out can also be a challenge. We can do the same sort of thing that we did with the FPGA by reaching in and then using sort of a lever action with your fingers to pull it out. Again, like that. And again, it's very important that you don't pick up one end of it because you'll bend the pins that way. We've also got special tools used for removing ICs. So this is just called an IC puller, and it's designed so you can reach under the chip and then squeeze and gently rock, and it should just pop the chip right out. You don't really want to use pliers, but occasionally you can use something if you have to reach under, to pry gently underneath one end or the other, and again, you don't pry too far so you don't bend the pins. As long as you're careful, your chips will last for plenty of uses, putting them back in and out of the board. But if you do bend up the pins, often with a pair of pliers you can get those straightened out, as long as you've only done it once.
Okay, while that picture is still on the screen, notice on that particular breadboard that the red and the blue lines on the outside edges are not continuous, which means that the 2 halves of the board or the 2 ends of the board do not have continuous power. So you'll need to put a jumper wire between those 2 gaps in order to extend the red all the way down or the blue all the way down. And we'll see that. The board I'm using does not have that, but many of the boards do. So just remember that. Otherwise, you won't have power on one end of the board, and that makes it a little bit difficult to get the chips to do what they're supposed to do. Okay, talked about some digital principles, how we make things work, and then compare digital to analog just a little bit, because they are quite different in the way we approach it. When I went to my first computer school for the Air Force way back in the dark ages, I had a real problem with this because I was a very much an analog person. I would tend to think analog on everything, and at that time we were using a vacuum tube computer as our training model. It used minus 10 volts for false or low, and it used plus 30 volts for a high. And so I was trying to trace voltages through these different schematics and such. And actually on a test, one of the instructors who was more interested in teaching and having people learn than in passing tests actually taught me through that and explained to me, don't worry about the voltage levels, just think highs and lows. So that's one of the big differences. I did that, and then the whole picture changed for me, and I did very well in the class after that. So in the analog world, of course, voltages can vary between either one of 2 extremes. For example, if we have a light with a dimmer switch on it, the voltage out of that dimmer switch can vary from 0 volts all the way up to whatever the supply voltage happens to be, anywhere in between. However, with digital, we only have an on or an off. So with a digital, it'd be more like a conventional light switch. Either the light's on or the light's off. With analog, it can be on, it can be off, it can be dimmed anywhere in between. Digital only has two states, as we say there. It's on or it's off. It's a 1 or it's a 0. It's a low or it's a high. It's a true or it's a false. And we use those terms interchangeably, by the way. You'll see us go back and forth. And again, as we said, if we're using the light example, the light's either on or it's off. There's nowhere in between with the digital world. Digital counting. How do we count using ones and zeros? Well, it's not really that difficult. This is all based on powers of 2. If you remember from your high school math, when we do powers, any number to the 0 power is 1. So 2 to the 0 is equivalent to the decimal value of 1. Any number to the first power is the number itself. So 2 to the first power is 2. 7 to the first power would be 7, for example. And then we go into squares and cubes and quads and so forth, as you can see there on the slide. So we have 2 to the 0, 2 to the 1, 2 to the second, 2 cubed, 2 fourth, and so forth as we go through. Now, normally we think in terms of math, counting our numbers, the big numbers on the left, little numbers on the right. We do pretty much the same thing with our digital world. We put the least significant bit or the least significant value on the right as well. So as we see there in the next to the bottom line, or next to the bottom bullet, 2 to the third, 2 to the second, 2 to the first, 2 to the 0. It's normally how we would look at that. Now, as we go through there, we'll see, as we said, we'll see the least significant digit on the right. 2 to the 0 is a 1. 2 to the 1 is 2, and I'm in the very lower right corner of the slide. 2 squared, of course, is 4, and 2 cubed is 8. So that will represent the values as we go along. Now let's look at that a little bit deeper. When we count, for example, here's 0, 1, 0, 1, digital, and my screen kind of blinks in and out, so if I pause, bear with me. That's saying that if we, again, looking from right to left rather than the way we would normally look. So that right-hand 1 means 2 to the 0, or a value of 1. The 0 means we have no 2 to the first power, so it actually is a 0. 2 squared, of course, is 4, so we have a 4. And then 2 cubed is a 0, meaning we have none of those. So we just basically add those together. So 4 plus 1 is 5. So that 0101 would have a decimal value of 5. If it were, for example, 1111, all ones, that would mean we have 18, 14, 12, and 11 added all together would be 15, which means then, but using 4 bits, which each one of those ones and zeros represents a bit in the digital world, we have 4 bits. We could have a value range of 0 through 15, which is 16 different values, or again, using powers of 2 if you wanted to look at it that way, 2 to the 4th power. Okay, going from there, 1 bit is a binary digit. Basically, in most places, we use 8 bits for everything we do. 8 bits is called a byte, spelled with a Y. In the old days of computers, if you remember the Commodore 64s and the VIC-20s and the Apple IIe and the Centaur Timex and several of those other different computers, they all used 8-bit processor chips. That was the cutting technology at the time, of course. Today, most of our chips are 64-bit processors, so we've come a long way in that sense. Nonetheless, 8 bits constitutes a byte normally, which will give us a value range of 0 to 255. So if we have 8 ones, we'd have a value of 255. And we'll see a little bit more of that along the way. Then if we want to have a larger number, we just start combining the bytes. So 2 bytes is usually considered a word, depending on the system. A lot of systems today use 4 bytes for a word instead. It depends on the designer's desire and what he or she wanted it to be. So 2 bytes would allow us to have a value of 0 to 65,535, which means we go from 2 to the 0 to 2 to the 16th. If we take 4 bytes as a word, that would give us a humongous value, 4,294,960,000. Whoa, can't say all that. A huge number, 295, which is 2 to the 32nd power. So we can make a number as large as we want it just by adding more bits to the left. Now, if we want to go negative, there's a special technique for doing negative. We're not going to talk about the negative world. We just add a bit and designate that as the sign bit. And we know that when we design our logic, and we keep that in mind so that we can deal with negative numbers if we need to. But we won't deal with the negative numbers. We'll just deal with the positive numbers today. So that's how we can represent huge decimal numbers just using ones and zeros. How about arithmetic? Because that's one of the big claims for the processors. They're able to process large amounts of data, do all kinds of math and other things. How do they do that? Well, this is binary arithmetic. 0 plus a 0 is a 1. 0 plus 1 is 1. 1 plus 0 is 1. However, 1 plus 1 is 1 with a carry of 1. Now, what do we do with the carry? The carry, just, as in regular arithmetic, goes over to the next position and is added in. So if we wind up with 1 plus 1 plus 1, it's still 1 with a carry of 1 to the next position. And we'll see this happen here in the next slide or two. And we go ahead and do that to the left for as many pairs as we need to make that happen. So looking at it like this, if we wanted to add 0101 plus 0010, now decimal values would be 5 plus 2. As you see there, the top number, we have 1102s and 14. So 4 plus 1 is 5. The second number, 0100, means we have 1, 2, no 1s, and no 4s and no 8s. So we add those together, we get 7 decimal, but when we add those together digitally, 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 1 is 1, and 0 plus 0 is 0. So we get 1, 1, 1, 1. You remember we said earlier, if we had that pattern, we would come up with a 7. If we had all ones in that whole thing, then we would have 15. Okay, taking it one step further. What if we add something that requires a carry here, such as 5 plus 5 in decimal? So we have the 5 plus 5, which we have 1, 1, 1, and 1, 4. 4 plus 1 is 5, gives us that. So adding it together, 1 plus 1 is 0 with a carry of 1. Into the second position, 1 plus 0 is 1. And we continue going that as we go from right to left. Again, 1 plus 1 is 0 with a carry of 1. 0 plus that carry gives us a 1, giving us 1010 in binary, which says we have 0 1s, 1 2, we have 0 4s, and 1 8. 8 plus 2 is, of course, 10. So it all works out. And that's how we basically do arithmetic using ones and zeros. And we can do the same thing with the other 4 functions in arithmetic for subtraction, multiplication, and addition. There's some other things that we do, but it still works basically the same way when we go through that. Digital decisions. How do we make decisions with this? Well, it's really not that difficult. We have things that make decisions for us all the time. When I want to go into my house, for example, I have 4 locks on my front door. I have a lock at the top and a lock at the bottom, a little flip security lock kind of a thing. Then I have a key lock in the door handle, and I have a deadbolt lock that uses that same key. In order for me to open the door, then I have to have a true open on the top lock, a true or an open on the handle lock, a true or an open on the deadbolt lock, and a true or an open on the bottom lock. Then I can open the door. So if I have the first open, the second open, the third open, the fourth open, I can open the door. We do the same thing with digital. If this is true and that is true, then the output is true. But if one of those is false, then the output is wrong. If I miss one of those locks, I can't open the door. It's false. And that's essentially what we're doing with logic. So we say if this is true and that's true, the output is true, generally speaking. Now, we can do crazy things called inversion and invert that so that it's always the opposite of what we would expect. Or we can go the other way with the inversion. As we said, if it's this and it's not that, then the output is false. If it's not this and it's not that, then the output is not that either, or it can be true if we invert it. So we can play with those combinations. When we get into the chips, we'll actually demonstrate that function so you can see it happen. We call this Boolean logic. That was named from George Boole, who came up with the idea, and it's used to express the different conditions. Digital integrated circuits are a great thing. They've come a long way. Of course, in the early days of transistors, we had a lot of discrete logic, meaning that circuits were actually made up with transistors and diodes and resistors and various things, all these discrete components sort of soldered to boards. Then over time, those came into integrated circuits in miniaturized form, so we could put many, many transistors and diodes and other parts in one little old tiny circuit. And that's what we have here. That LM 747 chip that you see there in the picture is a dual 741 chip. A 741 chip is an operational amplifier. It's a special kind of an amplifier that compares two inputs and gives you an output based on that to either combine or separate the inputs. Now, pin identification, if you look at that again, you see the little notch at the top of the chip, which means and of course this one also has the dot I see there indicating pin 1, so there's no doubt about which pin is pin 1. Now, one of the other little tidbits that we come to is this thing called pull up and pull down resistors generally. Generally, those pins on the IC will tend to float. They won't necessarily be high, being 5 volts, or they won't necessarily be low, meaning close to 0 volts. So in order to ensure that they don't go wild, we will put a resistor from that pin to ground, for example, to hold it low all the time. But since the resistor is there and it has enough resistance to allow it, we can put a high on that pin, and the pin will go high. We force it to go higher. We can apply a high to it, and it will still go high and stay high as long as that value, of course, is there. So that's generally how we condition things to make sure that we don't get any false readings out of our chips that we play with. And when we construct our circuits, we will actually put pull-down resistors. Sometimes you'll see pull-up resistors instead, where the resistor actually pulls the pin to the plus 5 volt supply to keep it high all the time. But again, with the resistor there, you can put a ground on that pin, and it will go to ground because the resistor doesn't allow us to short the power supply going through there. Power and ground, I missed that one. Power on these is normally 5 volts. Ground, of course, is the 0 volt point, of course. Now, we're using TTL logic, transistor logic, old style logic, which was made with transistors, diodes, and resistors. It uses plus 5 volts as its voltage. CMOS, which we'll talk about here in just a moment, the CMOS ICs use a different voltage. We'll cover that when we come there. This is a picture of a 7400 quad NAND gate. N-A-N-D, NAND meaning not and. What that really refers to, if you notice the little symbol, the little bubble-looking symbol there with a curve across the top, looking at the top left of this picture, on pin 11, you see a tiny little bubble and a curved surface. The curved surface under that indicates an AND gate. The little tiny bubble or the little circle indicates that we have inverted the output, meaning that we have knotted it, as we say. So this says that, basically, look at this. If we put a high in on pin 13, a high in on pin 12, we actually get a low out then where the bubble is on pin 11. Now, were that bubble not there, then we would put a high in on both 12 and 13. We would get a high out on pin 11. But since the bubble's there, that indicates the inversion or the NAND or NOT function, and it inverts it. Again, we'd put plus 5, called VCC, voltage common collector, which is an old term. We would put that voltage on pin 14, and we put our ground voltage on pin 7 for these particular series of chips. And we will be using this 7400 series chip in our demo a little bit later. Another chip that we'll use will be the 555 timer IC chip. It's a great little chip, does all kinds of things. It can act as a flip-flop, it can act as a timer chip, it can act as an oscillator, you name it. It's an 8-pin chip. You'll notice ground is on pin 1, and VCC, or the voltage applied, is on pin 8. And then have various other inputs that make it perform. And we'll see that happen as we hook it up in our circuit just a little bit later. Okay, VCC, is the old term, as we said, stood for voltage common collector. That comes back from the discrete transistor days, and we will apply that voltage to the collector of a transistor, so that's where that comes from. VCC just means the positive voltage that's being applied. With the TTL logic we're using, TTL meaning transistor to transistor logic, means it had transistors, diodes, and resistors actually. We use 5 volts for the power supply, and then a high or a true on that chip will generally be about 2.8 volts or greater. It doesn't actually have to be the full 5 volts. A low then will generally be 0, but it actually is more usually about like 0.8, 0.8 of a volt or a little less will actually be considered a 0 or a false. Now, the CMOS logic, we mentioned that earlier, stands for complementary metal oxide semiconductor. It was a special technique that was put together to allow us to use some different voltages and do some different things with ICs than we had done before on the voltage world. generally will have a VCC of about 10 to 15 volts. It can be quite a bit higher, as you see. And again, the signal levels, the faults and the highs are generally about the same for those chips. So that part doesn't change. Just the supply voltage changes. One other tidbit about CMOS chips: if you ever get a kit that includes a CMOS chip, it will normally be wrapped in aluminum foil, because those chips are very static sensitive. You have to be really, really careful with those. The chips we're using are not that static sensitive. They are to a degree, but not enough that we have to worry about it for what we're doing. Okay, digital integrated circuits. Again, we think in terms of ones and zeros, or highs and lows, or trues and falses, if you please, and not the voltages as such. The logic probe that I mentioned a little bit earlier is a nice little tool that we can use to indicate the highs and the lows, and that's especially true if the voltage is changing back and forth, if it's going from a high to a low, like from an oscillator output where it goes high, low, back and forth. The logic probe is good to indicate that. We could use a voltmeter to do that, yes, but then the voltmeter is going to be switching back and forth so quite rapidly, we might not be able to get a good reading if we're just using a voltmeter, hence the logic probe. Okay, generally, as we said, the one or the high or the true is positive. A zero, it would be a low or a false. Generally is the near zero volt or ground level. And then if we do negative logic, if we negate it or we not and it, if we talk with the NAND gates, then that all gets reversed and we flip everything upside down. Okay, we talked about tying pins high or low to prevent false inputs. The input pins will tend to float a little bit. So in order to make sure that we know what they're going to be at any given situation, we will tie a pin either high or low, meaning we take a resistor from that pin to ground, or a resistor from a pin to +5 to maintain a high or low state for it. Pull up, pull down resistors. Okay, to try to illustrate these, we'll look at some digital building blocks with this. This is an AND gate, AND meaning if this is true and that is true, then the output is true. So we're using switches here for the inputs to indicate that. So we have a voltage supply passing through two switches, a current limiting resistor, and an LED to indicate on or off. If the LED is on, then it's true or positive. If the LED is off, then it is false or low. In order to get that LED to light, we have to have S1 true and S2 true. We have to close both switches, so we have A closed, or S1 closed and S2 closed, then the light lights and we get a positive indication. That is, we get a true out. By the way, that little thing on the right is just a little tidbit. In identifying LEDs, LEDs have a cathode and an anode. The cathode is the little bar and the symbol that you see at the bottom of that LED drawing. There's a long lead and a short lead. The long lead will normally be the anode side, and the flat spot on the LED, if you can feel that, and some of the really small ones, it's hard to see that flat spot, would indicate the anode side, but we'll see that a little bit later when we get to it. So this is an AND gate. If S1 is true and S2 is true, then we get a true output, that is the LED lights. Then we have the OR gate. This is where we say if either one is true, we get a high out. And this might be one of those cases where you check your bank account, and if your money is above a certain threshold and you have permission, then you could go. That would give us the AND gate function. But if they say if you have money or you have permission, then you can go and look at your account. Either way, you can still look at your account. So this is the same kind of thing. The OR gate, again, we're using switches. So if S1 is true, the LED turns on. Or if S2 is true, the LED turns on. If both are true, it still turns on. But if both are false or open, we do not get an LED turn on. So it would be the output is, as we said, false. This diagram is not the best, but it's trying to illustrate the NOT or the inversion function. We're using a relay to indicate this. It's a little bit of a kind of a turkey in the way it was drawn. If I had drawn this myself, I would have done it a little bit differently. LED 1 and LED 2 are two outputs showing both sides, the high and the low. The idea behind this is if I close switch 1, then the relay there will close and pins S5 and S4 would come together and would light LED 2. But we're trying to light LED 1. That's our true indication. So when it is not closed, when S1 is not closed, the relay is in the position as it's shown, and LED 1 is lit, meaning that the switch has not been pressed. You kind of have to work with your mind a little bit there and think upside down to make that happen. S1 is open, so LED is turned on, meaning that S1 is false. A false in or a low in gives us a high out. It's inversion. The inverter symbol on the right is the little triangle. The little bubble there indicates that it has inversion. A high in gives a low out and vice versa. Were that bubble not there, then that would be an amplifier function. Whatever comes in is whatever would go out. But normally the inverter will be drawn just like that. There's the little triangle with a little bubble on the output. The bubble always means inversion. Excuse me. Okay, the AND gate, another picture of it here. If A and B are high, then C is high. If either A or B is low, the output is false. Then the not AND gate, we just put a bubble on the output, which was what we just talked about. So if A and B are high, the output is now low because it's been inverted. And you can see the effects of if the other outputs are, if either A or B is low. Then the OR gate is illustrated by that little curved block at the bottom. If A or B is true, then C is true. Either one or both, we're good. If both are false, then the output is false or low. If we wanted to invert it, we just put a little bubble on the output like that. Now we have inversion. If A is high or B is high, then the output would be low or false because we've inverted it. Okay, so now let's talk just a little bit about the flip-flop. We're not going to go in great detail on the flip-flop, but it is one of the critical building blocks is used in the digital world. The flip-flop, as you can probably gather from the name, means that you can trigger it some way and it will hold a high or a low or whatever you programmed it to do, depending on the type of flip-flop it is. Most memory circuitry that we see today, including the memory that's in a solid state, use this technique. They would use a flip-flop. We'll flip the flip-flop in one direction, giving a high out until we're ready to represent a 0. Then we'll flip it the other way and represent a 0. And since it sets that state and it holds it, it will hold it indefinitely as long as power is applied. And then, of course, there are special transistors that will hold it even when the power is not applied. But for us, in our case here, we're talking about when power is turned on. The two pictures we have there, the bottom one is a set reset flip-flop. We hit the set button. The top output goes high, the bottom output goes low. We hit the reset, it flips back the other way. So basically, it's just like a light switch we're turning on and off. We just flip it back and forth. The other is called a JK flip-flop, has all kinds of other things it can do. It can have a set pin, a reset pin, and a clock signal coming in. So the clock, every time the clock goes high, we can have it do something depending on what the set and the reset values are. Will determine what the outputs are going to be. You notice on the right of that diagram, there's a little thing called a truth table or truth chart that tells us what the combinations can be. And we'll talk more about those truth tables here in just a moment. This is used exclusively for counting circuits. When we want to count, we use flip-flops to count things up and down. When we wanted to display different things with either with display numbers or with LEDs, often we'll use flip-flops to make those things happen. We'll set a flip-flop high or low to turn something on or off, and it will hold it until we change it back to something else. So, as I said, we're just going to mention flip-flops. They're a critical building part, but we're not going to delve into that to any great degree because otherwise we would have a whole class on just that. But there's that much to that kind of discussion. Truth tables or logic tables, as we talked about a moment ago, give us a way to visualize the inputs and the outputs of a particular gate. So this particular gate we're showing here is an AND gate. So if X is high and Y is high, then Z or 3 is also going to be high. And in the truth table, you see that represented. The first line in the truth table is 0 plus a 0 gives a 0 out. So a low and a low gives a low. A low and a high gives a low. A high and a low gives a low. But to get a high out, we have to have two highs coming in. Just a way to visualize how that gate is going to perform. Likewise, if we do the OR gate, we do the same thing. A 0 and a 0 gives a 0 out. Any one in, however, will give us a high coming out. One or the other or both would give us the high on the output. And then we put the bubble on the output of the AND gate, making it a NAND or not AND gate. It's been knotted, as we call it. And we see just the opposite of the AND gate. Now, any 0 in gives a 1 out. Any low in gives a high out, if you please. And 2 highs in are required in order to get a low out of that particular gate. Same thing with the not OR gate when we put the little bubble on the output of it. So now we see that we have to have both lows on the input in order to get a 1 out, but any high on will give a 0 or a low out. Just a way to illustrate it. So to practice this just a little bit, if you want to get your pencil and tablet and do this, by all means do so, but otherwise we'll show you a slide in a second that has it in there. This particular chip, 7420, is a dual quad input, not AND gate. Dual meaning there's 2 of these in one chip. And, excuse me, quad input just means there are 4 inputs. So looking at the gate on the top, the output for that gate is on pin 8. And you notice the little bubble there, meaning it's been inverted. The 4 inputs are on pins 9, 10, 12, and 13. So if we put 4 highs in, if we put high levels in on 9, 10, 12, and 13, we would get a low level out on pin 8. Any low in, however, would make us go to a high out on pin 8. So how do we illustrate that in a truth table? Well, let's look at it. Since I couldn't put all of that in one place, that's why it kind of spills over to the right in 2 columns. What the truth table then is illustrating is that in order to get a 1 out, I need a 1. I need a ones and zeros on the inputs. To get a 0 out, though, I have to have all 1s on all of the inputs. The only case where I can get a low or 0 out. So just another way, again, of illustrating how the chip is going to perform on making its decisions that we want it to make. Okay, now, we've talked a lot about the chips and some of the ins and the outs and all that. We have to have power. Without power, obviously, we're dead in the water. Let's talk about a bridge rectifier. In our AC class, we talked about using a half-wave power supply, just using a single diode. The problem with a half-wave rectifier supply is that you waste half of the sine wave. As you see the sine wave, the AC input on the top left, where our AC input is going positive and going negative back and forth, in America at a 60 hertz or 60 cycle rate. With a single diode, we would only use half that waveform, waste the other half. By using a bridge rectifier, we can use both halves. It makes it much easier to filter or give us a nice smooth DC out, which is shown in the right top half of that same picture there. You see the full wave DC output with a capacitor on it. Makes it a little bit easier to filter that. So we have 4 diodes. AC comes in on the 2 pins. You'll recall on the little bridge rectifier, there were 2 little squigglies which represent the AC input. Kind of looks like that symbol for AC. We put the AC into there, and then we have a plus and a minus on the bridge rectifier, letting us know which side the minus comes from and which side the plus comes from. Then it comes out of there, goes into a load resistor. That just makes it stable so that it doesn't bounce up and down. And then we put a capacitor there to filter it, to help fill in those gaps when the voltage drops as the sine wave goes back and forth. Now, we will in fact build one of these here just in a minute to show how that actually works. Okay, we're going to breadboard up the power supply. We're going to use a full wave bridge rectifier. We're going to try to keep the components on one end of the breadboard for this because we're going to put chips on the other end of the breadboard and we need that space. Reiterating, there are 2 AC input markings, the plus and the minus marking. We want to be sure we get everything polarized correctly and get the 2 AC, little squiggly marks there in the right place as well. And then we'll connect our little transformer to that so that we have AC input. I have some little 9-volt AC transformers, 300 milliamps, so they're very low power. That's on purpose. If we accidentally short that thing or we short components, it's not going to burn anything up or cause any kind of a safety issue. So that protects us just over. Okay, now we're going to build our bridge rectifier circuit and then run that through a capacitor, put the little the little resistor on there. We'll also add an LED and a resistor as a power indicator. So starting out, I have my breadboard. This particular breadboard, as I said, the rails go all the way through, so I don't have to put jumpers in the middle, but that's neither here nor there. There's an old jumper, I'll take that out. And there is my little bridge rectifier. You can see the two little squigglies indicating AC on either side, the positive on that side. The other side doesn't have a minus. Many do. This particular one does not, but that's the minus side. So what I want to try to do here is put this in the breadboard so that the two AC pins come here and the DC pins go into the next row. It just kind of keeps everything nice and clean. Then I can take the output of there, add the capacitor to it, and then go on down with the line there, adding the components. You'll notice that the legs on this thing are bent terribly. There's a reason for that. That's so that they will actually go where they're supposed to go. So let me see if I can make this happen. The two squiggly leads are these two right there. So I'm going to put those two, I hope, right in there. Okay, now let me see if I did that. Okay, squiggly lead and a squiggly lead. Okay, so my AC is going to come in on the ends. And then I'm going to use my little pliers here to move these leads. It's easier than putting my fingers in there. I'm going to put this lead in the next row down, and that's where my DC will come to. I want to make sure those are in good. And then put the other side in on the next row down again, like so. And then I'll make sure none of the leads are touching each other and they're away from each other like that. Okay, so we have that. So now, if I put my AC in as I had intended, and I take my trusty voltmeter, okay, now let's go to voltage. And I'm going to check that voltage output. The plus is supposed to be here. The minus is supposed to be here. And I'm showing about 5.5 volts. Now, that's pulsating DC at this point, okay? So I'm going to disconnect my AC for right now, just to be nice. Then I'm going to add a capacitor. I have here a 1,000 microfarad at 50 volt capacitor. You'll notice the stripe on one side, which means it's polarized. That'll go to the negative side of the circuit. Obviously, the other will go to the positive side. So for me, the positive side is over there. Negative side is over here, so I'm going to have to do a little bit of creative bending to make this fit. Okay, so the positive is going to go in right there. And the negative is going to go into the negative side. There, like that. And I kind of lay it down like that a little bit so it doesn't get, hopefully nothing will get in my way there. And then I'm going to put a 1,000 ohm or 1K ohm resistor, which is a brown, black, red. I have to watch where I am on the camera there. Across that as well, that's going to be my load resistor just to stabilize it a little bit. So I'm just going to kind of piggyback that one across, like so. Okay, and again, being a little bit cautious to make sure I don't short anything out there. Now, let's see what happens to our voltage now when we measure our output voltage. So I'm going to go to the minus side here and the positive side here. Now we've got 8 volts. The reason for that, before we were measuring a pulsating DC, now we're measuring a filtered voltage, which gives us about 7.5 volts DC. Of course, the 7.5 volts DC is still a little bit much for our integrated circuit, so we'll fix that here in just a moment. Now I want to add a power indicator to that. So I'm going to take an LED and a resistor. I have to have the resistor because I need to limit the current that can flow through the LED. And I'm going to go here again from the negative side. And I'm just going to try to jump her across here, see if I can find an easy pin to get to. Now at this point, I'm going to kind of move around a little bit to a different pin just to make it easy to plug into so I don't short anything and everything's out of the way. Okay, so I've got my resistor. I really should have disconnected power, but I didn't. And then, okay, let's see, that's negative, and I need to go from here to the positive and flip it around the other way. Sometimes seeing what I'm doing is a little tough too. There we go. Okay, so I now have an red LED to let me know when I have power on. Hopefully that will remind me of what I'm doing here so that I don't lose fact and start doing a lot of circuit changes without disconnecting the power first. Okay, so I now have my little power supply as it's shown in the diagram that we looked at a little bit earlier. And we have an indicator showing what we're, where we are with that. Now we want to add a regulator to that, and that is this little guy here. This is a 7805 regulator. The 78 series regulators come in this type package and are rated at 1 amp continuous, 1.5 amp peak. There's 7805, the 05 indicates it's a 5-volt regulator. There's 9 volts, 12 volts, 15 volts, et cetera, a whole series of these. And then there's a companion series called the 7900 series. So 7905 is a negative voltage regulator. So this I'm going to insert on the positive side. The 7905 I would insert on the negative side and regulate from the negative side. So we're going to use the positive side. When I hold this like this and I look at the pins with the labeling up, pin 1 will be on my left. The ground pin is in the middle. The output pin then is pin 3 is on my right. So I'm going to insert this like this. My positive side, and hope I don't get my head in the way here. So I have my positive voltage coming out at the second row there. So I'm going to use that right there. And I should disconnect it, shouldn't I? I need to follow my own advice, you know. And those leads are a little bit big, so they're a little hard to get to plug in, but they're okay. Okay, so I put pin 1. Let's see if I can point it out this way. So my pin 1 is right there on my positive side output, which is this lead coming right across that row of pins. Okay, now I've got to put a ground on the middle pin here, though, to make all that work. So I'm going to need a jumper wire for that. Let me grab a jumper wire. And we use these little jumper wires. Sometimes they don't go in very well, and we'll use the pliers to push them down. It depends on how cleanly the ends are cut and how tight the pins are in the breadboard, of course. So I need to go from that pin ground, the center pin, which is the ground pin right there. Yeah, it didn't look like, yep, okay, then it went in. And I have to take this across to ground over here on the other side, which will be right here. Okay, so now I've got my 8-volt input there, the ground on there. The output from that then should be 5 volts. Let's check it and see. So I'll plug it back in. Light comes on, says I have power. And then when I check this, I'm going to go to ground and +5, that one, and get the leads out of the way. I hope. excuse me, I'm having a hard time getting those leads out of the way where you can see the meter. And it says my output is 5.08 volts, close enough for 5 volts anyway. So now we have a regulated 5 volt coming out. Next thing I want to do is distribute that voltage so it comes down the rails on the sides, because I'm going to have 2 ICs down here and I want to tap that power for that. So I'm going to use jumpers again to make that happen. Get me a couple of little jumpers here. And we have all kinds of lengths and sizes and colors and whatevers. Okay, so I'm going to jumper the output from that over here to the plus rail on the board, so I can have plus going all the way down there on the red line. Assuming I can get that to go in there. Okay, so I've now I now have 5 volts positive on that side, but I got to have the ground on the other side, so we're going to have another ground wire. And again, I've got to go from the ground from the chip, or from the regulator, and I'm going to take him over to here and plug him into the blue line. Like so. Okay, so now if I have it correct, I should have 5 volts over here on this bus. And it's not happening. And my leads are getting tangled up on me. What did I do wrong? And this is where real life comes in. Okay, I've got 5 volts there. And I got to get down to the pin. There we go. Okay, so now we've got it. So we've got 5 volts over here, negative over here. Now, I'd like to have another indicator, and I like to use yellow just because I like to use yellow, to indicate the voltage out from the regulator. So I'm going to do this. I'm going to use a yellow LED, and again, I have to use a 1K ohm dropping resistor or limiting resistor, brown, black, red. And I'm going to jumper that LED across from the positive to the negative on the rails, which will let me see my power. And I don't know, can we see that in the video? It is, you know, like that. That way you can see it. It's not really bright, but you can see that I have yellow. So now I know from looking at this, see it blink. Now I know from looking at this, the red indicates I have raw power, the yellow indicates I have regulated power, and we've accomplished a whole lot at that point. The next thing that we're going to do is build the 555 timer oscillator. That's this little tiny chip here that we showed in a picture earlier. We have in our handouts, there's several pictures of this. I'm going to be using a handout so I can see this. You'll recall that the little mark right there, that little tiny circle, is pin 1. So I'm going to just pick a place and plug him in. Now, since he's been plugged in before, he'll plug right in. Normally those pins, as the little video showed in the beginning, those pins will be set kind of at an angle. And you have to squeeze them in just a little bit so it'll go down flat. But this one's been in enough times that it's okay. Okay, so I have the chip there. And now I'm going to have to hook up power and ground. I need to hook up plus 5 volts to pin 8. Now you remember, as we look at the pins, that's 1, 2, 3, 4, 5, 6, 7, 8. So pin 8 is going to go to positive. And let's see, what's a good length jumper for that? Let's see if this will work. I can use one shorter than that for that. We keep them kind of short. It makes it a little bit neater. Okay, pin 8 is VCC. That is pin 8. That's the wrong row. Okay, so with that, so I have the positive rail coming here and going to pin 8 right there on the IC. And I probably should, in fact, move the power while I'm doing that. And I'm getting ready to power up the IC, and I really don't want to be messing with that until I get everything hooked up. And then we need to put a ground on pin 1 on this side. So we're going to go across here to ground. Let's see if we can use a brown ground wire for that one. So we're going to go, that's a little bit long, isn't it? Let's see if we can get something a little shorter. Sometimes we use green to indicate ground as well, so that's probably not a bad idea. So we're going to go from there to ground. Okay, so we now have power and ground on that chip. Then we want to put a jumper between pins 4 and 8. That's, if you watch the schematic, you'll see that the reset pin is being tied high. So between 4 and 8, a number of different ways I could do that. So pin 4 here and pin 8 over here, I'm going to just put a jumper in like this and just take it around like so and plug it in like that. So I have my jumper between pin 4 and pin 8. Okay, and then we need pin 1 also to go to ground, which we've already got. So we're good on that one. Then we need to jumper pins 2 and 6 together. So pin 2 right here, and pin 6 would be, let's see, 5, 6 back there. So we got to jumper those together. Again, I'm going to use I'll use another brown jumper for that and see if I can go do what I did before. So we're going to go from pin 2 around here to pin 6. Use the little pliers because it's easier. Okay, pin 5, pin 6. Okay, so put the jumpers between pins 2 and pin 6. Moving right along. We would normally put a small value capacitor between pin 5 and ground. That's a stabilizing capacitor. It will work just fine without that, so I'm not even going to worry about that particular one right now. Okay, now we're going to set up our time constant components. There's going to be 2 resistors and a capacitor. If you look at the schematic for this, let me turn my page here just a moment so I can see it. If we look at the schematic for this, we're going to use a 1K resistor as a current limiter, and then we have a resistor of 470,000 or 470 K ohms in series with a capacitor of 1 microfarad. That 470 K ohms and the 1 microfarad is a time constant setting pair. That is to say, they will set the time at which the LED will be on and off. And we'll talk about that here some more in just a minute. So right now, I need to get another 1K resistor. Okay, nope, that's not a 1K. Brown, black, that's not a 1K either. Come on, resistors, 1K, brown, black, red. And then I need a 470K, which is a yellow, violet, yellow. I've got those 2. And then I need a 1 microfarad capacitor, and that's this tiny little guy right there, which is kind of an interesting piece just by comment. The marking is 105. What does that mean? If you go back to our metric system, we want 1 microfarad, which would be 0.00000001 farad. And we go to nanofarads, and so that number actually is dealing with nanofarads. It's saying 5 zeros in there, meaning nano. We're not going to go into any great detail of that. So I've got those 3 components. Okay, I'm going to take my first resistor, R1, goes from power. Okay, right here, go to power to a connection point, like so. And then the 470 K ohm resistor hooks to him and goes to another connection point. And these are just, I'm not picking any particular points other than that they're available. They're not hooked to anything else. And then the capacitor goes from that to ground. So the capacitor goes from that resistor over to ground. Let's see if I can separate those leads enough to go direct without another jumper. Okay, so I'm going to go from there to ground, just like that. Okay, so we got the 1K, 470K, the capacitor between power and ground. as the schematic shows. Okay, now we got to put some jumpers in. We're going to put a jumper from pin 7 to the junction of the 2 resistors to here. Pin 7 would be way up there. So we've got to put a jumper from there to there. Don't need a real long jumper for that. Let's use a different color. Let's try a yellow one. So we're going to take this yellow jumper and go from where those 2 resistors join, which is right there. And we're going to take that to pin 7 with a little bit of luck. Pin 7, there we go. Okay. So we have the resistor now from the 2 resistors join right there and that whole row right there. So jumper from there over to here to pin 7. 1, 2, 3, 4, 5, 6, 7, making sure I've got the right count there. Pin 7. Then we want another jumper for where the 2, 6 goes to, remember jumper pin 2 to pin 6. We want a jumper from there to the junction of the capacitor here. So we're going to go from there to here. Very short little jumper for that. Shouldn't be a big problem. What'll fit good there? Let's try. Let's see if a little orange jumper would do that. So we can go from the pin 2, 6 junction to the junction of the capacitors and the resistors. In the case where it doesn't want to go down in the hole. Come on now. There we go. Okay, got it. So that was the jumper between pins 2 and 6 there to the junction between the 470K resistor and the capacitor. Okay, that should be everything that we need to do. We're going to hook on power. And see what happens. Now, what happened? Basically, nothing. How's that for a way to go? Now, what we're supposed to have at this point is a square wave output at about a 1 second frequency out on pin 10. But how are we going to know if we have that or not? Well, I could use my voltmeter like we talked about before, so let me just do that. So I'm going to take my voltmeter and go from ground to pin 3. And it's just holding a steady 4.5. It's not really showing me anything there. If I use my logic probe, let's see if it may show the same thing. We'll find out. Logic probe hooks onto ground and hooks onto plus 5 volts like that. And I don't know if you can hear the little buzzer. It has a little buzzer in it when it goes high. Okay, and it's staying high all the time. It should be blinking and going on and off. So that means I did a boo-boo somewhere. What did I do wrong? So my voltmeter actually wasn't lying, was it? Okay, I'm not getting my charge discharge. What did I do wrong? And this is part of the real life of a course like this. Now we get to go back and do a little troubleshooting and say, okay, what did we do wrong? What happened? Okay, I'm going to pull the power from it just to be on the safe side. And I'm going to back up and check all the different connections and make sure I connected everything like I thought I did. So I'm going to go back to the beginning. Okay, here we go. Pin 8 goes to power. Pin 8 goes to power. Make sure that's down good. And in just a moment, we'll double check that with a voltmeter and make sure that we do have power on the actual chip, just to be sure. Make sure our jumpers are all in good and everything's working correctly. Okay, and then pin 1 over here goes to ground, like there, and goes over to there. That looks good. And then pins 4 and 8 get tied together. So pin 1, 2, 3, 4, with that jumper right there goes to pin 8 right there. That looks good. We've already tied power to pin 8. Got that one. And ground on pin 1, we've got that one. And we got pins 2 and 6, 2 tied to pin 6, and we got that, okay. We didn't bother with the small cap. We could have put that in there, but we didn't on pin 5. It really doesn't matter. And then we got R1, which is the 1K resistor goes to power. Guess what? It doesn't either. Look at that. See what I did? I missed the rail. I got it. It should be in this hole and not that hole. So I don't have any power on that side to charge the capacitor. That probably is going to be the problem, would be my guess. Okay, well, let's just stop there. If that doesn't do it, we'll come back and check something else. So we go to here, turn on the light again, take this and go back to pin 3. Pardon? Oh, sorry, thank you. I have to have power on that. I'd removed it to make it easy to see a little bit earlier. Nothing's happening. And I do have power. Yeah, we got power everywhere. Power there. Okay, we're charging and discharging. So pin 3 should be doing the same thing. There we go. And that's what should be happening. You can see the little lights going back and forth on the probe indicating high and low. It's going back and forth at about a 1 second rate. We can actually calculate that if we wanted to. If we multiply the capacitance in farads of the capacitor and the resistance of R2 in ohms, multiply those two together, that will give us the time constant of the amount of time that LED will stay on. If we wanted to slow it down some, which I'm actually going to do here in just a second, if we wanted to slow it down a little bit, we could either increase the value of R2, the 470K ohm, or increase the value of the capacitor. I don't have another capacitor. However, I do have another 470K ohm resistor. Isn't that convenient? Before I do that, though, let's put us an indicator on that so we can see what it's doing. So let's take our another little LED and place right there. And another 1K ohm resistor. And I don't know if I can go that route or not, but I'm going to try. I have to watch it. I don't get a short circuit right there. And I probably got it backward. Well, no. Actually, again, it helps if I plug in the right row. Nope, I'm not getting anything. What's happening here? Okay, I must have a flaky connection somewhere here.
Yellow LED is going on and off, so it's your loose connection.
Okay, I'm getting it there. Why is my LED not doing its thing? Could I have a bad one? I guess anything's possible. Well, not sure why I'm not getting a blinking LED there. Probably because I think I'm going the wrong way. I think I need to go to ground with that instead. Let's go to ground instead. There we go. Whoops, to get the right connections. Now we've got it. Sorry, I put the LED to power instead of putting it to ground where I should have put it in the first place. So now I can have the indicator there showing my blink rate. And it's actually working. So what I'm going to do now is I'm going to add another 470K ohm resistor in series with this one, and this should make this about half as fast as it is right now. Disconnect this so it don't get in the way. Take that out. Move this resistor here over a little bit to places nothing's being used. Take my other 470K and plug in series with it. Go back into the capacitor again. It's going to look a little hokey, but I think it'll work okay. Okay, so I just added another resistor in series with that one. I basically doubled the resistor. And you'll notice the blink rate is about half of what it was previously, which is what we want. It's a little easier to see. It was blinking on and off so fast. Whoops. And when I lose power, I lose power. Okay, I've got a flaky connection somewhere. I think my AC pin may be flaky. Yep, okay, I got a loose pin on the board there where that AC is plugging in. Okay, so anyway, that's what it's supposed to do. So at this point, what have we done? We created our initial raw power supply. It gave us a raw DC output, just basically filtered. Then we went through a regulator chip to regulate it down to a +5, so we get a nice steady voltage. Put LEDs to indicate that we have the voltages there. We added the 555 timer chip, which gives us a nice square wave output. If we were drawing that wave, we would see it go up and down, make a nice square wave. And we can follow that by watching the little LED blink on and off. Now we're going to go talk about an OR gate circuit. Remember, the OR gate is if A is true, RB is true, then the output C will be true. So for the OR gate, we're going to use the 74, can I read that from here? 74LS32. The LS just means low power Schottky, which means it doesn't require as much power to operate this particular chip as some others might. And, excuse me, the Schottky circuitry is a much faster circuit than without it. So it's a fairly high-speed chip. Not that we're after speed in this case, but that's what I had on hand. And it's already been plugged in a time or two, so it should plug right in. Famous last words. Maybe it will, maybe it won't. Okay, so we're going to do the trick that they showed in the video. Lay it this way and just rotate it just a tad so that the pins line up a little bit better to plug in. And there he is. Okay, so we got our 7432 quad OR gate plugged in. Now let's see if we get some power and do some other things. VCC or power goes to pin 14. Pin 14 will be on this side. So I think I can use a short jumper for that. So we go from power to pin 14. And I guess realistically, before I go too far, I should shut the power off, shouldn't I? Not good applying and remove power when we're still doing the wiring. Okay, so power to pin 14. And then we want ground to go to pin 7. Is that right? 14 and 7. And I have a picture of that IC. Let me make sure I'm saying that right. Yep, 7 and 14. Okay, and ground goes to pin 7. Where's me a short jumper for that? Okay, remember the counting. There's our little notch there. We're indicating pin 1. 1, 2, 3, 4, 5, 6, 7. So we're going to go from 7 here to ground over here. Okay, so we now have power on the chip. Then we need to hook up some indicators so we can see what we're doing. Okay, we're going to put 2 pull-down resistors on pins 1 and 2. So we'll get 2 more 1K resistors here. 1K and 1K. Okay, and we're going to put those on pins 1 and 2 to ground. Remember 1 and 2, starting here, 1 and 2 go to ground like so. And again, 2 to ground, just like so. Okay, so we now have those 2 pins grounded. And then for the output, we're going to use another LED and a resistor, of course, to indicate the output on pin 3. So pin 3 is also going to go to ground. This is going to get a little tight here. But I think we can squeeze them in there. Oops, that's not a 1K. Pin 3. And put that into the lead. It goes to the LED. Kind of spread them out just a tad. Now, if I didn't put the LED in backwards, that should work. We got 2 lows in on an OR gate, should give us a low out. So let's put power on and see what we've got here. Okay, go back to our logic probe again. Okay, checking that. Now, on pins, pin 1, we got a low. Pin 2, we got a low. And pin 3, we've got a low, just as we would expect. Okay, with a low, that means the LED would not be lighted, correct? Now, we want to take another jumper. Use a different style, just a second here. Makes it a little bit easier. And I'm going to take 5 volts right off the 5-volt bus, and I'm going to apply 5 volts to pin 1, like so. And when I do, that should make it switch states. Right now we're low, and it goes high, just like it's supposed to. So any high in gives us a high out, just like it should. However, my LED is not indicating that, which means I probably have it backward. I'm a little backward anyway, so that's kind of normal. Come on, get in there. Okay, now then, let's take one of the inputs high again. And we see the LED come on. If I go across both of them, make both of them high at the same time, we still get the same indication. So either one in is a high, we get a high out, high in and high out, high in, high out. Now, if we want to make it a little more interesting, how about if we take the output from pin 3 over here on our IC, that's where our little square wave's blinking, this LED, and we put that into this input, guess what we get? So we're basically using this as a generator to give us a signal on pin 1. Every time pin 1 goes high, pin 3 goes high, we see the LED work. And of course, I could move this over to pin 2, it would work the same way. And when I remove it, of course, the LED goes off, just as it should. So the OR gate function works as we would expect it to work. But what about the NAND gate, the not AND gate? Well, let's demonstrate that chip. We got to change chips for that one. I've got my handy little chip puller here. So I'm going to just slide that right under like so. Pull it. Turn off the power. Yeah, I should turn off the power. Thank you, Lance. Remind me to do what I'm supposed to. When I forget, I get carried away. You definitely should turn off the power when you're doing that. Absolutely, you should. Okay, we're using a 7400 series chip, 7400 quad NAND gate. However, I don't have any 7400s. What I have here is a 5400 series, which is a mil-spec chip, which you'll notice is a ceramic case. It's a harder, higher temperature case. The one we were using before is a little plastic case very light duty by comparison. But I just happened to get a surplus deal once upon a time, so that's what we have here. Now, the pinouts, fortunately, are the same between the two chips. Power and ground are on the same chips. Inputs and outputs are on the same pins, rather. So I'm just going to plug this right back in where the other one was, and we should be good to go. That way I don't have to rewire everything from scratch. So now we have an AND or a NAND gate inserted. Remember, with the NAND gate, if I put a high in on both inputs, I'll get a low out. And that's what we should see happen at this point. Now I will put the power back on. Yes, Lance, don't let me forget to connect and disconnect. I tend to get carried away and forget who I am sometimes. Okay, so at this point, I've got a low in, which we can see here. Got a low and a low, and I've got a high coming out, just as we would expect. Now, what if I alternated one of those pins from the output of my little oscillator, just like I did on the other chip? Let's do that. Okay, so I've got one pin now going high, low, but the output is still staying low, isn't it? Or still staying high, excuse me. So this shows that it is low, just as it should be. Or I'm sorry, it's going back and forth. So this is a NAND gate. That means I'd have to have both pins going high and low, wouldn't I? So how can I do that? Well, I could put a funky jumper, I guess, across those. That's going to be kind of hard to do. So what I'm going to do is pull this. And I'm just going to kind of hold this jumper between the two. I hope. And you'll notice the LED goes back and forth just like it should. Now, but I'm putting going high, low on both pins, 1 and 2, at the same time. I take it away, and we go back high again. Now, that's just demonstrating the not and or the and function, depending on how you like to define terms. What if I added another section as an inverter? Then this pin 3 output that we're watching here should be the opposite from that inverter. We can do that with another section of this same gate, which makes it really easy to do. Sorry, forget to talk to the camera sometimes. Okay, so we're going to add a little bit to this. We're going to add an inverter function. We're just going to use another section of that same chip. We'll just tie the 2 input pins together, basically. And so that will give us an inverter function using a NAND gate, if I can get that said right. And Lance didn't remind me, but I'm going to remember this time to take the power out. Okay. Now, I'm going to put my jumper pins 9 and 10 together here on the NAND gate. Let me get me a picture of a NAND gate so I can see that. So by jumping the 2 together, that makes it into an inverter, essentially. That's really all we're doing with that. So I'm going to jumper pins 9 and 10. How do I identify 9 and 10? Well, 1 through 7, 8, 9, 10. Oh, how convenient. So 9 and 10 are those 2 pins right there. Easy enough, right? So let's get a small jumper for that one. So 8, 9, and 10. Okay, so with that, I've jumpered 9 and 10 together. And then we're going to jumper pin 3. We're going to take the output of this chip from before, and we're going to jumper it to this input that we just created. So I'm actually going to use a fairly long jumper for that, just to keep things easy to handle. So pin 3 was the output right there. Okay, and I'm going to put that onto the input of pins 9 and 10. Okay, now 8 is the output, so I need another LED indicator to indicate what we're doing on the output. So I'm going to have to be a little creative here, because I've got to go down a ways to get to where I want to go, and I need another 1K resistor, which I just happen to have. Okay, whoops. Well, I just had it. I just dropped it. Oh, that's okay. I've got another 1K right there, so we'll look for that one later. So I'm going to take the output, which is on pin 8 right there, and go to my LED to indicate its output. So what that's going to mean then is that when the output on pin 3 of the IC goes high, the output on pin 8 should go low. So the LEDs should basically go back and forth. That's what we're saying with that. So we're going to see if that happens. Okay, so we got inputs, we got outputs, we got an LED. Let's see if we can put power back on and get things to play again. Okay, so we have the output right now is high, from pin 3. Okay, so a high in would give me a low out. The out, that should be off, and that is correct. Now, what if we put a high in? Let me get another jumper. We're going to pick us up a high right there from the power, and we put 2 highs in on the inputs here. That one goes off. This one should go on, and I probably got him hooked up backwards, so let me turn him around. And guess what it does? Okay. Now, if we want to get a little fancy, take the output from the oscillator again, and we're going to put it in on both pins of the first section of the gate back in on pins 1 and 2. I'm just going to hold those together here. They're hard to hold together, actually. And there we go. And you notice those 2 LEDs on the end, one goes high, the other goes low. The inverter function is working exactly as we anticipated that it was supposed to. Okay, so with that, what have we done? Well, we've gone a long ways. What all have we actually done? Let's go back to the slides, please, Lance, if we could. Okay, I'm going to go through, zip through some of these. This is just the instructions that we followed while we were making all this happen. Okay, we hooked everything up. There was our triple nickel. There was our circuit that we actually implemented. And I'd back up a minute. I did not follow my own caution as I should have, as you'll notice there, to take the AC power off. I forget to do that a couple of times. Fortunately, Lance reminded me, and I'm glad that he did. Just good practice. Again, the schematic, what we were doing, the instructions on how to hook it up, how to hook up the OR gate. That's the demonstration that we did with that. You remember, any high in on 1 or 2 gives a high out, makes the LED light on the OR gate. Then we pull that chip out, and we put the 7400 NAND gate back in its place. And for this one, because of the bubble of inversion, we have to have 2 highs in to get a low out, or vice versa. So we demonstrated that. Then we added another section and used it as an inverter using this schematic. You'll notice that pins 9 and 10 are tied together. So basically, it just makes an inversion. Whatever goes in one pin is in the other pin. So it inverts. The high end gives a low out, vice versa again. And we saw that with the 2 LEDs on the output. One goes high, the other goes low, exactly as we expected that it would do. And then we hooked our little timer circuit up to it, our little oscillator circuit, and we could see it blinking the lights back and forth, just like it would. So what have we done? Well, we built and we demoed the power supply. Then we added a regulator to the power supply. We added indicators to each of those so we could see that we had power. Then we built the oscillator circuit and saw its square wave output. That is, it's going high and low. We looked at the time constant on that. By doubling the value of the resistor in that time constant, we slowed down the blink rate, made it a little bit easier to see. Then we hooked up the AND gate, actually the NAND gate technically. We demonstrated the OR gate first, then the NAND gate, and then the inverter function. Now, I don't know about you, but I enjoy doing this. To me, this is just a lot of fun. And I would encourage you to do the same thing. These little breadboards are very inexpensive. You can buy those on Amazon. Matter of fact, I bought 3 the other day just so I'd have some new ones. There were 3 for about $7, so they're not real pricey. And likewise, you can use any kind of wire that you have to make the connections. You can buy different components very inexpensively and wire these things up and play with it. And if you get a jam, call me. I'll give you what I've got. I'm happy to share with you because I have plenty of this stuff. Where do we go from here? Well, it all depends. A lot of things that we can do, a lot of possibilities on the horizon. Jerry and I have talked about this. And some of the classes we have a components class, which is kind of a combo class of the DC circuits, AC circuits, and the solid state. We go through the different components, what they do, demonstrate them, measure them, play with them a little bit. We talk about capacitors, resistors, transformers, coils, transistors, etc., and go through all the different components and just talk about those from a component standpoint. We also are looking at doing some kind of a troubleshooting class where we maybe bring in some things that we know are not working correctly and see what it takes to make them work. And maybe adding a few common tasks that we all need to know how to do, such as checking power out on a radio or checking SWR on an antenna. So there's some possibilities with that. We have a vacuum tube class. People wonder, well, why would I want to do vacuum tubes? Because the principles in vacuum tube circuits are essentially the same as the circuits we use today in solid state. And in that class, we trace a receiver circuit through. The principles of a receiver for that vacuum tube circuit are the same as the circuits we use today for the most part. The oscillators are a little different in how we generate a frequency, but other than that, the mixing principles are exactly the same. So it's a good class from that standpoint, and see what goes on with vacuum tubes. And there's still a lot of vacuum tubes equipment out there. Many of our amplifiers for HF are still vacuum tube. So there's a lot of possibilities. We can also do some kit building. There's all kinds of kits available inexpensively. We can also build a little radio from scratch if we want to do that. We literally take the parts and use a piece of board from Hobby Lobby and wire up an AM radio circuit on that board and actually make it work and do all that in one setting. So there's lots of things that we can do from that. Anyway, I've enjoyed doing this. I hope you will enjoy this and get something from it as well. Have a good time along the way. Hey, go build something. Take care.